We just finished up talking about inorganic nomenclature and went through quite a variety of different rules and different types of inorganics. Just briefly again, we talked about the binary compounds, meaning two elements, and of course we talked about binary nonmetal compounds. We talked about binary metal with a nonmetal, and in that case we had two different types of metals. As you recall, we had those metals that had only one charge, which were the elements in row 1, always a +1, and elements in row 2, or column 2, always a +2. Aluminum +3, zinc and cadmium +2, and silver +1. The rest of the metals then, all of these included down in here, the rest of the metals we had to use a Roman numeral to tell what the charge was on the metal. We then went in to talk about metal polyatomic compounds. So we were talking about a polyatomic anion hooked to a metal. Again, we have the two types of metals, and we looked at the ways of naming those. We looked at the polyatomic anions hooked to hydrogen and talked about the polyatomic acids. We also talked about ammonium compounds, which are somewhat unique from the standpoint that we consider the ammonium ion, the NH4 plus ion, as being the same as though it were a sodium or a potassium ion. So even though it is made up of two different elements, we still considered it and named it in the same way, especially when we attached it to the nonmetals. We named it with an IDE ending, just like we did with the binary metal nonmetals as well. Well, one of the things that the last part of the chapter looks at is a little bit more on the nomenclature of organic chemistry. Now, we've looked at it several times. We looked at how we named hydrocarbons, and we looked at how we named alcohols, and we looked at how we named ethers. So we've looked at several different categories of organic. This chapter focuses in on those that we refer to as aromatic, which includes the compound that we've already mentioned in organic, benzene. And this particular chapter looks primarily at what we call substituted aromatic compounds. So benzene compounds then with things replacing some of the hydrogens on the benzene ring. And so we'll take a little look this morning then at a couple of the organic compounds and something about their nomenclature. Once again, we have talked about this particular one. We talked about it when we said polyunsaturated. Those that have multiple double bonds in it are referred to as polyunsaturated hydrocarbons. So we have carbons with alternating double, single bonds, and then of course the hydrogens. Each carbon has 4 bonds to it, so it's satisfying the octet of electrons that we talked about in the chapter on chemical bonding. But rather than writing it out this way each time, it's typically written in this form here, just the hexagon with a circle in the middle, which then is representative of the benzene molecule. So whenever we see that, we know that we started with a benzene. We might then selectively take off some hydrogens here and substitute other things in place of those hydrogens, but the basic shell structure remains the same, the 6 carbons with alternating double single bonds. Well, one of the compounds that we can look at then is the first one here that we see, in which we have taken now one of the hydrogens from the benzene structure and replaced it with a CH3. A CH3 would be known as a methyl group from our organic chemistry we've talked about before. It's a methyl group, and actually we could name this methylbenzene, would be one way to name it. But again, in organic chemistry, we have a lot of common names, and you're more likely to see the common names when you're working in organic chemistry. If you went on and took a course in organic chemistry, you'll see a lot of the common names. And the common names for this one, with the CH3 replacing one hydrogen, so there's still 5 hydrogens around there, is called toluene. Toluene. But we do notice the ending, the ENE, of course, which is the ending that we use in hydrocarbons to represent molecules with double bonds in them. Remember, ANE means that everything is carbon single bonds. ENE means that we have at least one carbon-carbon double bond. And the YNE, the ine ending, was used if we had a carbon-carbon triple bond. Now, toluene can be reacted with nitric acid, and we can produce a compound, and I'm going to redraw this one. If I find my clean sheet here. I'm going to start with toluene once again. So we have the basic benzene structure and the CH3 to make a toluene. Now, if we react toluene with nitric acid in the presence of concentrated sulfuric acid, which acts as a water remover, what we'll end up doing is putting on 3 NO2 groups. So we're going to take off 3 more hydrogens here now, and we're going to put on these 3 NO2 groups. And this compound is called of course obviously for the 3, trinitrotoluene. Trinitrotoluene, abbreviated TNT. Anybody ever hear of TNT? I'm sure that you have. This, of course, is one of the major components of explosives. Now, we talked about one other explosive, the one that the Nobel family was famous for, and that was nitroglycerin. Nitroglycerin is somewhat similar in this overall structure, but it was made from glycerin, and which we then put on NO2 groups. Now, glycerin, of course, is an alcohol, remember, an OH, so it was 3 alcohol groups on there. And we do this, we put in the NO2s like that. And so we see that we, in fact, have, there would be some hydrogens here, we, in fact, have then 3 NO2 groups, just like we have 3 NO2 groups in TNT. But TNT is much more stable chemically. So when we talk about dynamite or dynamite sticks, oftentimes it's made with TNT rather than nitroglycerin. Nitroglycerin, of course, as the Nobel family, or Alfred Nobel specifically, found that you could stabilize this by absorbing it into cellulose fiber, wood, sawdust, cotton, things like that, that would help stabilize it. But this is much more shock sensitive, temperature sensitive, etc. And part of the reason is this oxygen bond here will break fairly easy compared to this carbon-nitrogen bond in TNT. And once we start breaking chemical bonds, energy begins to be released, and actually this here provides the oxygen so that the carbon and hydrogen can be converted then ultimately to carbon dioxide and water with a lot of release of heat energy. The same happens up here, but it is much more stable, and so it takes a good kick to get TNT to begin reacting. Once it starts, it releases a lot of energy, and so it is a good explosive, and it reacts fairly rapidly, but it is much more stable. Trinitrotoluene. Again, toluene is the benzene ring with that CH3 group on it. One of the ways that we name some types of substituted compounds, benzene type compounds. And here I have kind of crammed in here, but here are 6 benzene rings, and in each case we've taken off 2 hydrogens and replaced it with 2 bromines. Now, one of the ways that we did naming before is we numbered the carbons, and we could still do so. In the benzene ring we could number, and it doesn't make any difference where we start. We usually start where the first attached group is, and we could number 1, 2, 3, 4, 5, 6. And actually, in this particular example that I have here, we could then number 1, 2, 3, 4, 5, 6, and we always number to give the things as small a total number combination as possible. We could call this 1,2-dibromo for the BRs, for the bromine, 1,2-dibromobenzene. That's one of the ways that we could name it. So benzene would be our base name, and then 1,2-dibromo. We have 3 possible isomers of dibromo. Notice all of these will have the same chemical formula. They all have 6 carbons, 4 hydrogens, and 2 bromines, but they're isomers of each other. They're actually structural isomers. Well, previously we talked about cis and trans structural isomers, and that's all right in a linear molecule, but when we have a cyclic molecule, we can't use cis and trans because that won't tell the possible locations of everything. So one of the ways that we named the isomers in this particular case, if we don't want to use the numbering system, is we use the prefix ortho if we have 2 substituted groups side by side. We have meta as a prefix when we have bromines that are alternating. In other words, there's one space in between the bromines. And then we use the prefix para when we have the 2 attached groups across from each other. And so this could be called ortho-dibromobenzene, meta-dibromobenzene, and para-dibromobenzene. And so that is another type of prefix that we can use to name isomers when we're dealing with then the substituted benzene rings. That would be if we're putting 2 attached groups that we're naming. Now the one in the center here with the 2 chlorines, this one would be called para-dichlorobenzene. Para-dichlorobenzene, this one right here. Para-dichlorobenzene. Remember, in organic nomenclature, when we write names, we just write everything together. The only thing that we separate out are like numbers. We might say 1, 2, dash, but everything else is all hooked together. Unlike inorganic chemistry, we wrote potassium and then a space and then chloride. We didn't just lump it all together. All right. But in organic, everything is just written as one word, para-dichlorobenzene. Anybody heard of para-dichlorobenzene? Anyone ever hear of mothballs? I imagine most of you have. There are 2 types of mothballs on the market. Mothballs, of course, are chemical that we put in with clothing when we store it to keep moths from eating it, especially true of clothing that contains wool, which is attractive to some types of moths. And we have naphthalene. That was one of the earliest mothballs, naphthalene, but it had a very, very strong odor. And then we have para-dichlorobenzene, and most of the mothballs today is para-dichlorobenzene. If you pick up a box in the grocery store or hardware store, or wherever you might be looking at it, just look at the ingredients on there. Primarily para-dichlorobenzene. Para because they're across from each other, and of course there are 2 of them. This particular group right here when it is used as an attached group is called phenyl, the phenyl group. That means that we've taken a hydrogen off right here, and we're going to use this bond now to hook it to something, so that we could hook these benzenes now to a hydrocarbon chain or whatever the case might be. As a matter of fact, we saw one of these in polymers when we had this hooked to a carbon, kind of like that, and every other one had one of these phenyl groups attached to it. So we had alternating carbons with phenyl group. That was called styrene. And when we hook it together and make giant molecules, polystyrene. Again, there's a common name. But oftentimes in organic naming, we call this group here the phenyl group. For instance, here we have the phenyl group hooked to an alcohol, and we call it phenol. We drop the YL and substitute the OL. So the phen means this benzene structure, and then the OL means the alcohol. Actually, we pronounce it phenol, but it's phenyl from that particular benzene and then the alcohol. All right? So this is an example of an aromatic alcohol in this particular case. A couple of other types of compounds involving this phenyl group, or the benzene group. Here we have put on now the organic acid group. Remember, the organic acid group is a carbon with a double bond oxygen and an OH on it. So this is the carboxylic acid group that we talk about in organic chemistry. And then we have the benzene ring. So sometimes it's called, in terms of phenyl, phenolic acid, or it's also called benzoic acid. Benzoic acid. Benzoic acid is used as an antioxidant in foods. So if you look on food labels, oftentimes you will see, especially if it's a food that's exposed to the air, breads, jellies, things like that, that you're going to open and then they're going to have contact with oxygen. Benzoic acid is a food preservative. It's called an antioxidant. It will tend to scavenge up oxygen and help prevent food decay. A slight modification of this, notice it looks like benzoic acid except for one thing. We have replaced one more hydrogen with an OH. This is called salicylic acid. Salicylic acid. And this is one of the two major components in preparing a chemical compound called acetyl salicylic acid. And acetyl salicylic acid is the #1 medicine in the world. Anyone want to guess what its common name is? Aspirin. So this is one of the major ingredients. As a matter of fact, a little later in the chapter on oxidation reduction, we'll come back and look at the chemical reaction that puts together then the acetate, the acetic acid part, and the salicylic acid to give us this new organic compound called acetyl salicylic acid, common name aspirin. Here's a chemical that no longer can be used in the United States. This is called dichlorodiphenyl trichloroethane, abbreviated DDT. Okay, the first D stands for dichloro, that means these two. And then the second D is diphenyl, that's the two phenyl groups that I was just talking about, the other name for benzene. Trichloro, 1, 2, 3 chlorines on a 2-carbon structure ethane. So dichloro, diphenyl, trichloroethane, or abbreviated DDT. Now, pesticides in general are organic compounds, and most of the pesticides halogen-containing organic compounds. And one of the problems that we have associated with the halogenated hydrocarbons is that they are fairly chemically stable. In other words, once we put them into the environment, they tend to stay for a long time. There aren't natural occurring microorganisms that easily break down these chlorinated compounds. And that's what was the problem with DDT. DDT was used primarily to control mosquitoes. And it was very important in, for instance, the tropics during war and things like that, where we needed to spray and protect the soldiers, etc. DDT was very important. But what happened is it turned out that in the natural food chain process, DDT tends to become accumulated. And the last in nature was the large birds of prey, the eagles, the large hawks, things like that were eating the rabbits and the mice and things that were eating the grass and the grains, which now were containing DDT left over. And what happened is then all of a sudden the DDT interrupted the shell-making ability of the birds. And so what was happening is that the eagles, and that were laying eggs, falcons, etc., would lay eggs, but the shells were so thin that in the nesting process they'd crush them. And so suddenly there was no reproduction. There were no young eagles being produced. They were essentially wiped out in the nesting process. So we have outlawed. Matter of fact, most countries have now outlawed the use of DDT. There are still some third world countries that are using it to control mosquitoes because of the concern of malaria, and it's justifiable. Malaria kills a lot of people, and one of the ways to control it, of course, is through the use of DDT. One of the compounds that's been produced to substitute for it, which you can now buy and use, and is used to control mosquitoes, etc., is this compound here called 2,4,5-T. Well, the 2,4,5 stands for the position of the chlorines on the benzene ring. So if we go right up here, this would be the number 1 carbon, number 2, 3, 4, 5. So we have then 2,4,5 trichloro, and notice that this structure right here, I would hope that you would see this part. If I break right here and here, that's an oxygen in there. What kind of compound am I basically dealing with? R-O-R. Anyone? R-O-R. We know that R-OH is an alcohol. What's R-O-R? Ether. So we're looking at an ether here, but the 2,4,5 stands for 2,4,5-trichlorophenyl, and then this part over here, and we see another functional group right here. There's an acid on there. Actually, it's acetic acid, but there's the acid group. 2,4,5-T is the common commercial name for this particular insecticide, which is allowed. Even though it also has chlorines on it, it is more biodegradable than DDT is. And so there are organisms that will break the ether bond, will start to chop up this, and we have much less problem with extended chlorine in the atmosphere. Here's a chemical that if you happen to work in a hospital or something like that, you might encounter. This is called hexachlorophene. Now, the name hexa, of course, would mean 6, prefix for 6, chlor, 6 chlorines, and the phene would be the phenyl, or that benzene type structure. All right, and we see that its general structure is, here's the 1, 2, 3, 4, 5, 6 chlorines. We've got a couple of alcohols on there, and we actually have 2 benzene rings hooked together through this CH2 group. Hexachlorophene is used as an antiseptic in the hand washing soaps, etc., used in hospitals. It's a very good, strong antiseptic. So it has very, very important commercial use in the medical field. Most of the scrub down soaps, etc., in operating rooms, hexachlorophene. So again, however, some problems can result, but not from the hexachlorophene itself, but in the production of hexachlorophene. Quite unknown to the chemist at that time, we could end up producing a byproduct which looks like this. Again, notice that it still has the two benzene structures. Now has 4 chlorines instead of the 6, so we pulled 2 off. We took the alcohol and used them to attach the 2 rings together. And this has a common name of dioxin. And so one of the problems in producing then this hexachlorophene was that dioxin was being produced as a waste product. Well, of course, we know here in Missouri, part of the history of it, this hexachlorophene was produced in Aurora, Missouri at a plant. And a person owning a horse ranch and a trailer park in Times Beach, Missouri, was buying the oily waste product from the Aurora plant and trucking it up there and spraying it on the ground to prevent dust in the roads and dust in the trailer camp and dust in the horse barn area. Well, the first thing that was noticed that the horses were becoming sick and finally they were dying, and investigation then finally narrowed down to the fact that they were succumbing to this particular chemical, dioxin. As a matter of fact, this is the most toxic organic chemical that we know of. It has an LD50. That means that 50% of the animals or species would die if they were subjected to 10 to the minus 6 grams of dioxin per kilogram of body weight. And a kilogram is about 2 pounds. So for a normal human, that would mean that about 0.00001 gram of dioxin, 50% of the humans, now this is on, of course no one has tested this, this is a proposed limit, that 50% of humans subjected to that level would die from the dioxin. However, a lot of controversy over dioxin. We know that it kills rats, we know it kills horses. There's been not one single case that a human being has died from dioxin. Not one. Not one single substantiated case of human, even sick, that could definitely be pointed to dioxin. So it may be that biologically this is not a toxic substance for humans, but it's very difficult to get 100 humans to volunteer to eat dioxin to find out if it is or isn't. But the person that actually did a lot of research on it is so confident that humans are not susceptible, literally ate grams of dioxin to show that there was no toxicity. Now, that might be that one person isn't affected, but again, we cannot test this on humans. But this would be the level based on this as the LD50 based on animal studies. It's one of the most toxic chemicals we have. Well, again, it's a matter of risk analysis, and we have to make a decision. Can we gamble that it isn't toxic to humans? Well, if we're not certain, the safest thing to do is get rid of it, but we spend an awful, awful lot of taxpayer money to do so. The Big Blue Goose, which was a big incinerator that was built specifically to take dirt that has traces of dioxin and put it in this giant furnace and burn the soil up so that we burn up all of the dioxin and convert it all to carbon dioxide and water and chlorine compounds that are scrubbed out. And a lot of taxpayer money went to do so. But anyway, we've cleaned up Aurora, we've cleaned up Times Beach, we cleaned up a farm down by Aurora which before this gentleman was buying the oil, it was being shipped out to a farm, and this person used his farm, as he had the right to do, as basically a simple landfill. And he was taking these barrels of this waste material from the Aurora plant and burying it on the farm. Well, that has all been dug up. All of those barrels, all of that soil on that farm have been incinerated. All of the dirt, tons and tons and tons and tons of dirt have been plowed up, loaded, and burned in Times Beach. And Times Beach now is supposedly clean once again. All right, well, if you happen to drive to St. Louis, of course, just before you get to St. Louis, you pass through Times Beach right along the interstate. All right, turning to the last topic in Chapter 9 deals with a couple of industrial chemicals of importance to us. Number one industrial chemical, anybody remember? Mentioned it a couple of times during the year. What's the number one industrial chemical, number one that we can look at to tell how manufacturing oriented a country is? No one. All right. Sulfuric acid. You've never heard me say anything about sulfuric acid? I hope you have. Number one industrial chemical is sulfuric acid. The number two industrial chemical might really surprise you because of its relative abundance. Nitrogen. Nitrogen is the number two industrial chemical. That means that it is used in terms of tonnage, the second most used chemical in industry. Nitrogen. 80% of our atmosphere is nitrogen. Doesn't seem like it would be something that would be that important, but it is. It's very important. Boiling point of nitrogen is minus 196 Celsius degrees. That's pretty cold. To produce nitrogen, because most of it has to be purified from air, that's our major source, is done by what we call the fractional distillation of liquid air. We take air, we cool it and compress it, and liquefy it. At that point, we have a mixture of liquid oxygen and liquid nitrogen. We then slowly raise the temperature, and nitrogen, which boils at a minus 196 as compared to oxygen, which boils at a minus 183, the nitrogen boils off first, and so we separate it by distillation. So we boil off the pure nitrogen, recollect it, recompress it, and put it into nitrogen liquid. The major uses of nitrogen are to provide an inert atmosphere. So if we're doing welding, for instance, very sensitive welding where we can't have any oxygen get into the weld and make it weak, we need to surround it by an inert atmosphere. And nitrogen is used for that. For instance, if we're going to put in big oil pipelines across Alaska to transport the oil from the Alaskan Bay Area all the way down to, say, California for processing, we want to make sure those welds hold. And we don't want any weak welds due to the fact that oxygen in the air has reacted with the iron as we welded it and made a weak weld. And so it's welded under an inert atmosphere of nitrogen. Food is stored. I think I mentioned this maybe earlier in the year. Fresh apples. I mean, we can buy apples today. We can buy apples several months from now. We can buy apples year-round that are relatively fresh, even though they're basically all picked in. If they're American apples, they're basically going to be picked in November, October. But yet in March, we can have fresh apples. Well, the thing that makes food spoil is oxygen. And so when you buy an apple from the store and you put it in your refrigerator, yes, you're keeping it cool. That slows down spoilage, but it's in contact with oxygen, it'll spoil. It'll ripen also. But if we keep oxygen away from food, it won't spoil and it won't ripen, and so we can store it for long periods of time. So apples, potatoes, etc. are stored in an inert atmosphere. Take a room like this, you'd fill it full of apples, you'd pump out the air, flush it with nitrogen, and store it under a nitrogen atmosphere till you're ready to come in and haul some out. Quick freezing. Well, at minus 196, you can freeze things quite quickly. And most of the food that is frozen food is quick frozen by running it through then a bed of liquid nitrogen or liquid air to freeze it quickly. When things freeze slowly, what happens is you start one little tiny water or ice crystal, and all of the freezing occurs on that one crystal, so it gets very large and it expands. And when that happens, just like what happens to streets and roads in the wintertime, when water freezes, it expands, it ruptures, it breaks things apart. Quick freezing, however, doesn't allow big crystals to grow. What it does is it makes millions of little tiny crystals of water, and they don't expand and grow and rupture. And so the texture, the cell fibers of the foods then aren't torn apart, and we end up then, of course, with a much more palatable, natural tasting type food. The earlier, if you just normally freeze food when you thaw it, it gets pretty mushy. If you slow freeze, you just stick something and put it in a freezer and let it freeze, you're going to end up with a pretty mushy type of food when it thaws out. But quick freezing prevents this because the water freezes in many, many little crystals and doesn't rupture then those cell walls that give the structure. And probably the most important is in the production of ammonia through reacting with hydrogen. And the hydrogen is obtained primarily from natural gas, CH4, and we get ammonia. And of course, ammonia is used to make ammonium and ammonium nitrate, so various types of fertilizer. And ammonia itself is used directly for then that purpose. Okay. Well, I think we'll save the number 3 industrial chemical for just a minute, because I did bring down some liquid nitrogen and I wanted to show a couple things with the liquid nitrogen here. Seeing I have it here, we'll go ahead and do that quickly. As I say, liquid nitrogen is relatively cold. Minus 196, so that's a little cooler than normal. So I'll do a little protection here in the process. Now what you see there is that's liquid nitrogen that's pouring. That's just pure N2 in the liquid state. The steam above is the moisture in air that's condensing. That's not liquid nitrogen. And I'm hoping to get enough in there that... Yes, I have. Okay. Things change properties a little bit when we subject them to minus 196 degrees. And here, take a little daffodil, pretty little delicate, soft petals there, and we'll go ahead and we'll do a quick freeze. You might even hear the boiling because, of course, obviously when I stick that flower in there, temperature comes up and the liquid nitrogen now begins to boil. One of the uses of liquid nitrogen is in the storage of, a lot is used in agriculture for storing semen samples. So if you have a prize bull, for instance, you can get samples of the semen and put it in tubes, quick freeze it. It doesn't rupture the cells in the semen. It can be thawed out and placed then into the cow later. And you notice that really it doesn't look like anything different. It's still, but if I touch it now, you see it looks like glass, not a flower that you would normally think of anymore. So its property changed. Now the janitors will love this. So rubber band. We know that rubber expands, or expands, not expands, it stretches, relaxes. And we'll give it a little boil. So as I was saying, you could store, of course, the specimen for a considerable length of time and later use it for reproduction then in the cattle. And now we have the rubber band. And of course, if I grab it now and try to expand it, it doesn't do too well. It has become solid. In fact, it has very nice permanent shape in the process. I really wanted a racquetball, but all of a sudden I couldn't find any of my used racquetballs, but this is a rubber ball, and so we'll try it. It's one to release nervous tension where you sit and do this. So anyway, we'll give it a little cool down here. Now, of course, that's a pretty good sized ball, so it'll take a lot of boiling to get it cold and freeze it. I can pretty well tell when it has gotten down to the temperature of the liquid nitrogen itself, because the boiling will stop. So while I do that, let me reinstall the glove here. Yeah, I don't know if I've gotten it frozen yet or not, but I think we'll take a chance and see what happens here. Still boiling some in there, but let's take it out and see. And we'll see what it does. Well, it seems to have lost a considerable amount of its elasticity. As I say, a racquetball is what I wanted because that's air inside and you get just the outside rubber. But it dented. It'll come back into shape as it warms up some. But a racquetball will just literally fly a piece like glass again. Now, if you've ever gone to a dermatologist for a wart or a mole or something like that, they may have used liquid nitrogen to remove it. So by using a little tiny needle with a little tiny hole, they can direct then the liquid nitrogen on the surface of the mole, and of course freezing tissue will kill it. And then as it unthaws, of course, the tissue dies and the mole falls off. So it is used quite extensively in dermatology, because it does cause a deadening effect and finally killing the cells. And if I do this carefully, then at least I think I can do this. I always worry about this not going right. Okay. Anyway, I'm going to try to numb my thumb. Okay, now you know what it feels like if you get frostbite, but if I do it with liquid nitrogen, it's fast enough that I shouldn't get the frostbite. So I'll try it here. You can tell the confidence level is not real high at this point. Okay. It does tingle a little bit, but it's all right. Okay, heart's pounding a little faster than normal. But anyway, of course, if I get that numbing effect where I want it, just to show that, and one of the things they are now doing in microsurgery is to freeze an organ, and then it can be used or removed, etc., without any discomfort, essentially. So anyway, I think it's cold enough. I don't feel anything anymore. Okay. Okay. Now you probably wouldn't want to do that on an unfrozen thumb. Okay? pretty, it's starting to hurt though. So, all right, well anyway, we'll give it a little more freeze here. Okay, we'll try it one more time, see how. Oh, God. Ah, look at that, my thumb, I broke it right off. Oh, you don't think that's real, right? Well, see, it's not there. It's gone. Okay, but that's one way to surgically remove then organs, by freezing them so there's no pain. And then you want this meat here for later, for lunch or something? Okay. All right. Well, anyway, freezing objects in liquid nitrogen does make a difference. Oh, there's nothing to worry about. You're breathing it. It's part of the atmosphere. Those people up there laughed. They thought, he's down front. He's going to get it all. So, all right. Now the carpet's frozen for a minute. We get a nice little fog coming down the steps there. But liquid nitrogen is used for a lot of things. Number two industrial chemical. And really, I didn't lose my thumb, just so you won't go home worrying over spring break that Dr. Thielman's thumb fell off. One of the family of elements that we've been talking about in Chapter 6 is the family called the noble gas family. One of the elements in there, radon, has become of concern, or at least we hear about concern related to health problems of radon in recent years. Today I'm talking with Dr. Ralph Sheets, Professor of Chemistry at SMSU. One of Dr. Sheets' interests is environmental chemistry, and especially his research pertaining to radon chemistry. Dr. Sheets, can you explain a little bit how or where radon comes from?
Well, soil has uranium-238 in it, and that's radioactive. It decays, it turns into a metal called thorium, which is radioactive. It decays, and that goes on and on. Somewhere down the way, it decays into radon. Now, all of these things before radon were metals, and they stay in the soil, but radon as a gas comes out of the soil. Now, if it's under your house, then it comes up in your house, and if your house is closed, it tends to fill your house, and then we start worrying about it.
Ralph, if we do have radon in the air that we're breathing, what type of health effects can it cause?
Well, it's not really the radon itself that we're worried about. Radon is an inert gas. Therefore, when I inhale, do you see that? I inhaled. Got this radon in my lungs, but when I exhaled, it came back out. Now, since radon has a half-life of about 4 days, it didn't stay in there long enough to do much of anything. On the other hand, right here in this room, radon is decaying, and as it decays, it's turning into radioactive metals, lead and bismuth and polonium, and they are decaying. They tend to attach themselves to dust particles, so that when I'm breathing in the radon and the oxygen and the nitrogen, I'm also breathing in those dust particles. They come way down in my lungs, and they stay in here. Now, when they sit in my lungs here, they shoot out alpha particles, and that can cause lung cancer. Every year in the United States, there are about 150,000 people die from lung cancer. Most of that, we think, is due to smoking and tobacco. But the EPA estimates that about 10 to 15,000 people in the United States every year die from lung cancer due to inhaling radon, or better yet, the radioactive daughters of radon.
From my study of the elements, if I recall correctly, radon, if I remember, is a colorless and an odorless gas. This being the case, how do you go about detecting the presence of radon in the air that you're testing?
Yeah, it is colorless, odorless, tasteless. You can't tell it's there without specialized equipment. Now, there are several ways to analyze for it. The ways that I use, you can either analyze for the radon itself or for those radioactive daughters. If you analyze for radon, I have a little glass flask that's coated inside with a scintillator. You evacuate the flask, then you simply open it in a room and suck air into it. Now inside this flask, when those radon atoms decay, shoot out alpha particles, they hit the scintillator inside this flask, and that makes a flash of light. You can't see the light, but if you put it down in a dark chamber and you have a detector, then it picks up that light and it counts those light flashes for you, and you can tell how much radon there is. Now, on the other hand, if you're looking for the daughters, which is more what I do, you take a fan and pull air through a filter, and that takes them out on a filter. They then put this filter inside a counter, much like I described before, and count the flashes of light, and from that you can calculate what the concentration of the radon daughters in the air were.
Of course, as a scientist, you have the equipment necessary to make those measurements that you've been talking about. But as a common citizen, are there any testing kits, etc., available for the non-chemist citizen so that they can analyze to see if they may have radon in their home as well?
Yeah. You know, if you really were concerned and you really wanted to know how much radon you had in your house, there are professionals that you can hire to do that. Probably costs a couple of $100s. But if you want an idea of how much radon is in your home, best thing to do is to go out to a department store, a hardware store, buy yourself a radon detection kit for about $20. You bring that home. It's a little metal canister, so big around, so thick, and it's full of activated charcoal. There's a hole in the top with a piece of tape on it. So you take this thing and you put it wherever, and you record the time. You take the tape off. Now, while it sits there, the air diffuses in, and the radon is absorbed on that charcoal. After 2 or 3 days, whatever it tells you in that kit, you put the tape back on, you record the time, you mail it back to this company. All of that's included, the mailer and everything in the kit. And they put it in an instrument, and they read the gamma radiation, and then they send you a letter that tells you what the radon concentration was in your house at that time. Now, there's a magic number there we need to talk a little bit about. The units are picocuries per liter, which doesn't matter, but 4 is the magic number. The EPA says if that reading is less than 4 picocuries per liter, you're probably all right. Don't worry about it. If it's more than 4, you may want to worry about it, and the higher it is, the more you want to worry about it.
Dr. Sheets, if I did a test and I found that I do have an unacceptable level of radon in my home, what types of remediation are possible to take care of the problem?
Well, you know, every house is different. Some houses have basements, some don't. Some houses have leaky basements, some don't. So it really depends a lot on the house. But a general rule is that for many, many houses in which the radon level is not too high, an easy way and a cheap way to alleviate that is to use under-house ventilation. For example, you have a house with a crawl space. The radon collects in that crawl space, and then it diffuses into the house. But if you put an exhaust fan in the crawl space under the house and simply pull the air from the crawl space outdoors, that really keeps it from coming into the house. You can do that with a basement. You can even do that with under slab construction. And that costs, I don't know, several $100s, and then you have the expense of running the fan all the time. But that's probably an easy way to remediate most houses.
Dr. Sheets, I want to thank you for coming in today and spending some time with me and sharing with you some of your knowledge pertaining to radon and radon pollution, to share this information with my Chemistry 105 students and myself. And I want to thank you for your time.
Thank you.